Hey guys, so the second half of this chapter really is leading us up to solving trigonometric equations. So at the moment we're learning some tools that are going to help us that. So just now we've learned some new trig identities and we've looked at using those to simplify trig expressions. Now we're going to take a look at applying graph transformations to the trig functions. So it's going to be great fun. We're going to do 10 questions. We're going to do 4 on the sine graph, 4 on the cos graph, and then 2 on the tan graph. But the very first thing we're going to do is remind ourselves of the different types of graph transformation. So I've made some pretty pictures. These are available in the description down below, where they are in a PDF format. So hopefully they will be very useful. Okay, so our first type of transformation are translations. Now we get translations along the y-axis and translations along the x-axis. We can even smash them together so that we've got a combined translation. So translations move us up, down, left or right. So they change the shape of the graph too. Now, translations along the y-axis come from doing these two things to our functions. So f of x plus k moves our graph up k places, f of x minus k moves our graph down k places. I suppose we could talk vectors here as well for a bit of bonus information. So f of x plus k would move our graph by the vector 0, k. f of x minus k would move our graph by the vector 0, minus k. Then we've got translations along the x-axis. So whenever x is involved in transformations, it's usually quite counterintuitive. So this happens when our number k is inside the bracket with the x. So it's actually part of the function. It's not just being added on to the function. So f of x plus k translates our graph left. So the translation vector for that is minus k 0. Or if we had f of x minus k, that moves our graph positively to the right. So the vector would be positive k 0. So like I said, a little bit counterintuitive. Probably works in the opposite way that you expect it to. And then our combined translations look like this. So in general, f of x minus a with b added on at the end has the vector a, b. So that's our general combined translation. Okay, then next up we have stretches, squashes and reflections, which all come from doing the same type of thing to the function. So first of all, stretches, squashes and reflections along the y-axis. These come from multiplying our function by a number. So things of the form y equals k times f of x. Now, when k is greater than 1, this stretches our function vertically. So what happens here, every y value gets multiplied by k. So for example, if we had y equals 2f of x, any y values would get multiplied by 2. If k is between minus 1 and 1, so it's either decimal or fraction, then that squashes our graph. So it's like someone's putting their hands on top and bottom of the function and pressing it together. What happens here as well, if k is negative, then the graph is reflected in the x-axis. So again, we can think of k as our scale factor on the y coordinates, so every y value gets multiplied by k. Okay, then lastly we have stretches, squashes and reflections along the x-axis. So these come from multiplying the x inside of the function by some number k. So things with the form y equals f of k times x. Now, it's probably a bit counterintuitive again. When k is greater than 1, this actually squashes our function together. So it's like someone puts their left and right hands at the end of the function and presses it together. When k is between -1 and 1, so again it's either fractional or decimal, that actually stretches the graph along the x-axis. And again here, if k is negative, then we also get a reflection through the y-axis this time. So again with x, a little bit counterintuitive. Numbers greater than 1 or smaller than -1 actually squash our graph together, whereas fractional and decimal values of k stretch it. So, as I said, those 4 or 5 pages are available down below in the description box as a PDF. So feel free to download and use those. Right, let's start applying this then to the trig functions. Okay, so first out then we're going to do 4 examples on the sine graph, so it's a good idea to have a good understanding of the important points of the sine graph. So every question we do is in the interval -360 up to 360 degrees. So the graph sine of theta looks like this. So our maximum values are at 1, our minimum values are at -1. The x-intercepts are at -360, -80, 0, 180, 360, and the x-coordinates of our stationary points, so our peaks and our troughs of the wave, are at -270, -90, 90, and 270. So make note of that. We're going to be using that. I'm going to clear it up a bit. Let's do some transformations. Okay, first out then we want to sketch the graph y equals sine of theta minus 90. So let's first of all talk about what sort of transformation that is. It's going to be a translation because we are subtracting a number inside of the bracket with the x. So it's a translation. Now it's inside the bracket with the x. Now we're subtracting, so that's actually going to give us a positive translation to the right. So it's a translation of positive 90 along the x-axis. So the vector is 90, 0. So what I'm going to do here is put the important points on and then draw it off camera. We all know that I can't draw, so it's probably best the inevitable swearing doesn't make it into the video. So let's start from the left. -360 is now going to be translated to -270, and then the peak at -270 is going to be translated 90 to the right. The x-intercept at -180 is now going to be -90. Then we're actually going to intercept the y-axis down there, and then our next point is here at 90. Our peak then is at 180. Next x-intercept is there at 270, and then we're going to finish down there. So I'm going to connect that now. Okay, so here he is. So just make sure you label some important points. So I've labelled the x-intercepts and the coordinates of the maximums and the minimum down there. And we could do this guy over here, which would be at 360 minus 1. And also, don't forget to label your graph. So this is y equals sine of theta minus 90. Jobs again for the first one. Okay, for example 2, we want to sketch y equals 3 sine of theta in the interval minus 360 up to 360. So, what sort of transformation is this? We've got a number multiplying our function, so it's a stretch along y, the scale factor of 3. So what happens here, every y coordinate gets multiplied by 3. So nothing happens to our x values. So this point here, that would have a y coordinate of 1, is going to get multiplied by 3. So its y coordinate is now going to be 3, and the y coordinates of the minimums, which would be minus 1, are going to go down to minus 3. Down that. So we need one more maximum over here. So I'm going to join those points up. Okay, so there very roughly is what y equals 3 sine of theta is going to look like. So it's important here to realise the x-intercepts are all exactly the same. It's just the coordinates of the maximums and minimums. So this point over here would have coordinate minus 273, whereas it was minus 271. This guy down here would be minus 90, minus 3. This chap up here is now 90, positive 3, and this guy down here is 270 minus 3. So there's our sketch of 3 sine theta. Good times. Okay, next up, y equals sine of theta over 2 in our usual interval. So, what type of transformation is it? Well, we've got sine of theta over 2. So, it's a transformation of the form f of k times x. The thing inside of our function is being multiplied by k. So, the x values, which are really our theta values here, get multiplied by 1 over k. So here we've got theta over 2, so k is 1/2, we've got 1/2 theta, so our scale factor is 1 divided by 1/2, which is 2. So every one of our x-intercepts gets multiplied by 2. So this guy down here, minus 360, would be at minus 720, but that is out of our interval, so we don't care. This guy, minus 180, is going to move to 2 times minus 180, which is minus 360. This guy at 0 is going to stay at 0. 0 times 2 is still 0. This x-intercept here at 180 is going to move to 2 times 180, which is 360. Now what's going to happen here, this peak that would be at, or is at 91, is going to move to 181. So that's now going to be over here, and this guy down here that was at minus 90 minus 1 is now going to be at minus 180 minus 1. So those are our points. Now I'm going to join it up. Okay, so there is our graph. So this point here is now minus 180 minus 1, and this guy up here is now positive 180 positive 1, and that is our graph y equals sine of theta over 2. So it's stretched it along the x-axis. It's now made our graph longer. Important to notice, it hasn't changed any of the y values at all. Okay, let's do one more with sine. Okay, this time we're doing y equals 1/2 sine theta. So this time we have a number multiplying the whole function. So this is going to affect our y values. It's a stretch. Well, it's actually a squash. It's a squash along the y-axis. So it's a squash. How do we know it's a squash? Because the value is fractional. It's a half. So it's going to make our function half the size vertically. So it's a squash along y with a scale factor of 1/2. So nothing here changes with our x values, only our y values. So our peaks that were up at 1 are going to come down to 1/2, and our troughs that were at -1 are going to come up to -1/2. So we're still going to go through the origin. 0 times 1/2 is still just 0. So there are our points. I'm now going to join them up. Okay, so there is our transformed function. Y equals 1/2 sine theta. Let's just label the transformed points. So this guy now would be at minus 270 1/2. We got the same x-intercepts. So this guy down here would be minus 90 minus 1/2. Still through 0, 0. This guy is now 90 1/2. Still through 180, 0. And then this guy is now 270 minus 1/2. So that's our transformed function. Good times. Okay, now I've decided to make this a 2-part extravaganza. So in the next part, we'll look at transforming cos and tan. Hope you found this useful. Take care, guys.